When the chicken skin is crisp, turn over, along with the chicory. For the sauce.
I really don't understand this.
What do you mean?
He doesn't say what temperature to cook the chicken to. He doesn't say what material he's cooking on. He doesn't say what the heat flux is through the stove.
What are you talking about?
I only understand concepts of heat transfer as taught by Professor Landherr for CHME3312 Transport Processes 2.
What are... Heat transfer? This? It's a cooking show.
A cooking show lacking the important details on how to properly cook a meal.
Well, if you don't think Gordon Ramsay knows what he's talking about, go make your own cooking show.
First, I need to make sure that my cooking equipment operates at a functional temperature before I can start with any recipe, okay? First step in chemical engineering cooking.
So we're boiling water.
Yes, we are. We're going to use this boiling water to determine the heat flux of the stove at a certain temperature of... What the... High, medium, low. These aren't terms I understand as a chemical engineer.
Dude, just turn up the heat.
I need to know the exact excess temperature from saturation in order to determine the heat flux coming from the stove. Although, actually through an understanding of nuclear boiling, we can look at the approximate bubbling profile to create a rough estimate of where this excess temperature is. Alright, let's do that. So now we're going to turn the stove up to high, and now we're going to boil water.
So how does boiling water help you find the heat flux or whatever?
So, with nuclear boiling, which is when you have bubbles coming off of the surface of the material, you can use what's known as the Rosenau correlation to calculate the heat flux using known parameters of your surface material as well as your liquid material. So what we're looking for right now is the excess temperature of the surface of this pot from the saturation temperature of the water. Because this dials in some strange alphabet that's not Greek and I don't understand what it says, we will have to estimate the temperature. And the way we'll do this is by judging the type of nucleate boiling that's occurring off the surface of the pot.
So why are you stirring boiling water?
So one of the assumptions I need to fulfill to use the Rosenau correlation is I need to make sure all of my fluid is at saturation temperature. So I'm just going to keep mixing to make sure it's all nice and even.
So, this is chemical engineering, huh?
There we go. It's boiling. Look at that. Look at those bubbles form. If those aren't jets and columns, I don't know what are. Alright, I have my notes here from Professor Landherr for CHME3312 Transport Processes 2. And from what I can see here, jets and columns 10 degrees Celsius to 30 degrees Celsius. Those are some nice jets and columns, right?
Yeah.
So I can make a conservative estimate of about 20 degrees excess. Okay, so here we have our Rosenau correlation, which is used to determine the heat flux during nucleate boiling. So here we have our Q''S, which is our heat flux that's going into our liquid water to vaporize it. We also have some other intrinsic properties of water at saturation temperature, which is 100 degrees C here. Those values include our viscosity, heat of vaporization, density of liquid and gaseous water, our surface temperature, as well as our heat capacity and Prandtl number. These numbers can be found in the back of the CHME3312 Transport Processes 2 textbook.
Wait, you actually bought a textbook?
While the internet is glorious in that you can download free PDFs of all of these textbooks, I am a firm believer in participating and stimulating our economy. Also found in our textbooks are these CSF and N values, which are empirically derived coefficients that help account for the type of surface that the nuclear boiling is occurring on. In our instance, we're using a mechanically polished stainless steel pot, so we found values of 0.0132, for our CSF and 1.0 for N. So now we can evaluate our Rosenau correlation using our excess temperature of 20 degrees. Some of the assumptions we had to make include negligible heat loss to our surroundings from the heater, a clean bottom surface that was mechanically polished and is made of stainless steel. The water was at uniform saturation temperature. We have standard atmospheric pressure and our process is steady state. So when we plug in all of our values here, we get a final heat flux of 1.046 times 10 to the 6th watts per meter squared.
Couldn't you just use the glorious internet to look up the heat output of that specific model stove?
No. So now I have this cast iron pan that I want to cook my chicken with. However, I need to make sure that with this flux, that this cast iron pan does not burn my chicken, which I happen to know happens at 180 degrees Celsius. So doing some quick calculations, knowing the thermal conductivity of my pan as well as the thickness, I can determine the surface temperature of this pan with the particular flux coming out of that stove. So to find the temperature of the surface of this pan and make sure it's not above 180 degrees, which would burn my chicken, we can treat it as a simple slab conduction problem using the known flux that we calculated previously using the boiling water and known temperature of the heating element's surface of 375 degrees, which I found on the glorious internet. Making some assumptions such as steady state, heat transfer, no generation within the pan itself, constant thermal properties as temperature varies, which can be shown as an average 80 watts per meter Kelvin for the cast iron, and one-dimensional heat transfer. So starting with our heat equation, we can knock it down to our x term equaling 0. Doing some integrations, we can isolate our temperature terms, plug in our initial surface temperature and our previous flux to get a surface temperature of 124 degrees C, which is well below the burning point of chicken.
Isn't there some instrument that's sole purpose is to, I don't know, measure temperature? Like a thermometer?
Thermometers are for rich people that don't like to do math.
Alright, now I'm ready to use my knowledge from Professor Landherr's CHME3312 Transport Processes 2 lecture in order to cook my chicken at 1 million watts per meter squared.
Don't you need chicken for that?
Preheat oven to 400 degrees Fahrenheit. Clean the chicken. Pat the chicken dry. Season liberally. Garlic salt. Freshly ground pepper. Fresh thyme. Fresh rosemary. Turn stove flux to 1 million watts per meter squared. Oil pan with olive oil liberally. Place chicken on pan away from you. Beat around both sides for 1 minute each. Bake in the oven for 7 minutes each side, flipping in between. And enjoy.